yeah, I will try to talk about this topic that done in collaboration with Reinhold Egger in Düsseldorf, and I will present these two effects. So I will split the presentation into parts. First, talking about Mpemba effect. It is some effect that is based on the initial state preparation of systems, and then I will talk about the Pontus-Mpemba effect. It is some sort of effect based not on the initial state, but on the protocol for relaxation. So first of all, how many of you know what Mpemba effect is? Okay, some hands, not so many, but so let's start from the origin, and let's go back in time. We have to go back really early in time, and first of all, let's introduce it in the simplest way. So let's consider two copies of the same system. These two copies are exactly the same. For example, two buckets of water. They are totally the same except for the initial temperature that are different. One is hot and the other one is cold. And then we connect both of them to the same environment. It's a really cold environment below 0 temperature. And what we expect is that both of them will freeze after some time. We follow this procedure and we observe the time needed for both of them to freeze, Th and Tc. And of course, if we think about the phenomenological Newton heat law, we expect that the hot system will freeze in a longer time because it starts from a higher temperature, will exponentially decay in time, must reach first this temperature and then go down. So normal common sense will say that Th is greater than Tc, but when this does not happen, sometimes could happen that Th is the time for the hotter system to relax is smaller than the time for the cold system to relax. In this case, we talk about Mpemba effect in the classical way. And the story started really more than 2,000 years ago. The first one that wrote about this paper was Aristotle in meteorology, writing that the fact that the water has briefly been warmed contributes to its freezing quickly. It was some common sense known to everyone, but then this effect disappeared from physics for many years. And again, it popped up in 1400, 1600 with the experiment of Merliani and the definition of Bacon and Descartes that again introduced this effect. Again, the effect was forgotten in physics, but known in food industry and in some common knowledge, but not in physics books. And then we arrived to our days, when again, in 1963, an elementary school students in Tanzania, Erasto Mpemba, were late to prepare some ice cream at school for some experiment. So he took his hot ice cream mixture, put it in the freezer to gain some time, and he discovered that he freezes faster than the mixture of the other classmates. So he went to his professor saying, why the hot water freezes faster than cold water? And everyone started to laugh at him, started to take joke about him, saying that every time there was some mistake at school, it was Mpemba physics, Mpemba math, no one was trusting at him. But he was really focusing on this idea. So years by year, he asked this question to other people, till at high school, he met Osborne, after a lecture, he went to him and said, why hot water freezes faster than cold one? For the first time, someone said, okay, I don't know, let's see, I will go to the lab, I will make some experiment. Osborne went to the university, asked his technician, please do this experiment. The technician produces some data and said to him, I did it, but don't worry, I will repeat the experiment more and more till I will obtain the right result. But the result were always the same, and that were the one on this plot, where the temperature to freeze some bucket of water decreases when we increase the initial temperature. So Osborne went to Mpemba and they published together this paper, Cool, that is the paper that for the first time put Mpemba effect in the physics journals, and this is why we know it, we call it Mpemba effect and not Aristotle's effect. And the problem now is, but why this happens and when this could happen? So people try to do different explanations, at least for water, but none of this explanation was truly satisfying. And some really important contribution was given by Burridge and Linden that did some experiment and showed that Mpemba effect can be observed or not. It's a function of how we do the experiment, how we observe temperature inside the samples. So one must pay really attention to this. But they also discovered another thing that is really important. We don't need a phase transition to observe Mpemba effect. We can observe Mpemba effect just changing temperature, but staying inside the same phase. And this is really helpful in experiment. It will open the search for Mpemba effect in a wider class of systems. Right now, in water, it's not clear if it exists or not. People are still debating today. But in the meanwhile, it has been observed in many other kind of systems, like granular systems, spin glasses, and in the last 4 years, also in quantum system, both open and closed system. And we will focus on the quantum version of the Mpemba effect. a really huge theoretical contribution for the effect that try to explain why we have this effect came from Lu and Rad's paper, where they observed that when we give a kick to a system, when we do a change in temperature, we cannot expect to be able to define a temperature of time along the evolution, because the system is not anymore in a thermal state. So we cannot talk about a temperature as a function of time. Newton's law doesn't work anymore, indeed, and could happen that as a function of the initial state, the hot one or the cold one, as a function of the geometrical property of some effective potential energy landscape, the hot system could start from a position that is far away from the steady state, from the relaxation point, but following some route, some shortcut in this energy landscape that help him to arrive faster to the final point. So everything ends up in studying the properties of this energy landscape, and also to define some good function, it's not temperature anymore, to tell us how far we are from the initial state to the final state. So classical Mpemba effect is really difficult to detect, and people are focusing on quantum systems because they are much easier to be investigated. And indeed, in the last few years, there were many proof of the Mpemba effect in simple qubit experiment. People were able to observe it in a closed system, but also they observed it in a single qubit the inverse Mpemba effect that happens when we rise the temperature, or also the strong Mpemba effect that happens when the system relaxes exponentially faster. And what is the signature of the Mpemba effect in an experiment or in some theoretical study is something like this. We have some function that tells us how far we are from the equilibrium from the final state. We consider different initial state conditions. We let the system evolve, and we follow these lines. If there is some crossing such that the order is reverted, typically we talk about Mpemba effect. All of these are the experimental signature of the three cases I showed you before. So we have to look to some distance from equilibrium function, and we have to define it properly. Otherwise, we have fake detection, or we miss the Mpemba effect. So I will try to give a definition of the Mpemba effect in a quantum system for a wide class of system. In particular, the thermal Mpemba effect is for thermal states. So we have a system embedded in a larger environment that fixes some temperature or chemical potential. But we can imagine a more wide class of system where the quantum system is connected to more than one reservoir that act locally or globally. And if the properties of the reservoir are different, we can also have some current, heat current, particle current, or so on inside the system. So we go from thermal state to a more generic non-equilibrium steady state, that is a steady state, so any quantity is time independent, but we have some current across the system. And we want to generalize the Mpemba effect for this kind of system. So the formalism in which we work is the Markovian formalism. We assume that the density matrix of the system is described by some Limrad equation, where we have a unitary evolution given by the Hamiltonian, and some stochastic evolution given by interaction with the environment, described in terms of some Limrad jump operator that typically create transition from different many-body states of the system, with some transition rate that is the gamma. And we needed to introduce a protocol to detect it or not, and also to try to understand why it is possible to have an Mpemba effect. And already from this, looking at the Limrad equation, we can already understand why Mpemba effect is possible. We can linearize the Limrad equation and write it in as a linear differential equation. We can solve it in terms of the eigenvector and eigenvalues of the M superoperator that depends on the Hamiltonian and jump operator. And for large times, the solution is something like this. We have a first term that only depends on the eigenvalues with zero real part, that is a steady state solution, that is the same for all the system if you only have one. And at large time, we only have a contribution for the slowest mode. It is an exponential decaying contribution because the real part of all the eigenvalues of M are negative. And so, in this lambda, this eigenvector are fixed by the environment, not by the system. And the initial condition only enter here. So what happens? If we take a hot system and a cold system, and for some reason, the coefficient in front of this exponential is smaller for the hot system respect to the cold system, the hot system will be closer to equilibrium respect to the cold one. And this is why we have Mpemba effect in a Markovian system. It's really easy to give a theoretical prediction of it. The problem is that why this could happen and when this could happen. So, first of all, we want now to generalize the Mpemba effect. The classical Mpemba effect is in terms of temperature. We only quench temperature, but now we want to quench something else. We can quench any generic parameter of the system, but also more than one parameter. So we at time 0, we prepare the system in the steady state, that means in the solution of the linear equation, fixed by some list of parameters of the system. These parameters include the environment parameter, temperature, chemical potential, and so on, or also Hamiltonian parameter, magnetic field, and interaction strength, and so on. At time 0, we quench the system, we quench one or more of these parameters to a new set of parameters. For the classical effect, Mpemba effect, we just quench a temperature, but here we can quench anything else. And the system is not in equilibrium anymore, so we start to evolve, trying to reach the steady state corresponding to this new set of parameters. And now, as done for the classical Mpemba effect, we prepare two copies of the system that are exactly the same, except for some subset of parameters. And we prepare each of them in the steady state corresponding to different set of parameters. We quench at time 0 both of them to the same final state and see how they evolve in time. For the classical Mpemba effect, we only have temperature, but here we can have more. But when we have more than one parameter, we have also to define what is hot and what is cold, because now it has no sense to talk about hot and cold anymore. So now we talk about far and close with respect to some distance function in parameter space. For example, the Euclidean distance function that tell us which of the two copies of the system is the closer to the final quench or far away from the final quench. But then we also need to introduce another distance, a distance that tells us how far our system is from the final state. And for example, we introduce the trace distance that tells us how far the density matrix as a function of time is far away from the steady state solution of the linear equation. And we want to follow this evolution for different initial state. And if you think, and we use again this pictorial representation by Lou and Ratz of this energy landscape, we can have two kinds of cases. So let's consider some closed system in parameter space. So this is the post-quench parameter, this is the pre-quench parameter, and let's consider some far away system in parameter space. And let's put the corresponding steady states of these parameters in this energy landscape. So on this plane, we have all the hyperplane of all possible density matrix of the system. Two things could happen. One thing is that the closed system in parameter space is not the closed one in this energy landscape. So from time 0, the far system or the hot system is already close to the final point with respect to the blue one. So we'll surf around this potential landscape. And of course, as it starts from a closer point, we reach faster the final point. Quite trivial case, but this has been documented in the literature also for classical Mpemba effect. And then we have another case that is more interesting. Somehow the red point is far away in parameter space, is also far away in the state of system space, but for some reason the route it followed to reach the equilibrium is much faster than the route followed by the blue point. In this case, this distance is smaller, will be shortened in time, and for some time t star, this will find itself closer to this respective blue ball. In this case, even if it starts far away, it will reach the final point earlier. In this case, we have another kind of Mpemba effect. And we call it these two kinds of Mpemba effect, type 1 and type 2. The type 2 is the one a bit more interesting and difficult to find. So the signature is again something like this. Consider the blue and red colors in this plot like the close and far, cold and hot in terms of temperature, for example. Non-Mpemba effect, the cold system, the closed system is always, the trace distance of a cold system is always smaller, closer to equilibrium respect to the hot one. We have type 1 Mpemba effect when they are reversed at all time. So the red one is always below the blue one. And then we have the type 2 Mpemba effect when at the beginning the hot system or far system is far away respect to the blue one, but at some critical time they cross each other and the order is reversed. And the far system will reach equilibrium faster. So this is just the definition of all the possible kind of Mpemba effect we can find in a quantum system out of equilibrium. And we can think of some physical system that can show this effect, because this is just theory. We want to find some practical example. A really simple example is a Pullman-Kitaev model that corresponds to just two quantum dots described by this Hamiltonian. So we have some on-site energy, some interaction terms, some hopping terms between the two dots, and some superconducting term that destroy 2 electrons at a time or create 2 electrons at a time. And while the environment is described by some metallic lid that is able to inject or remove one electron at a system at a time. So we have a competition between the linear equation, between this Hamiltonian and these jump operators. And the environment will try to change by 1 the number of electrons into a system, while the Hamiltonian will try to keep the number of the parity of the number of electrons the same. So will trigger transition between different states, and the competition between these two effects can give rise to the Mpemba effect, the quantum Mpemba effect. So indeed, let's try to make the game I said at the beginning. We fix all the parameters, all the Hamiltonian parameter, and also the temperature and the chemical potential of the right lid. So we have two environments. We fix this one. We also fix the post-quench values of the left parameter. So we fix temperature and chemical potential of the left environment. And we consider different initial states described by different values of temperature and chemical potential. And we make a plot like this. So each point on this plot corresponds to a different initial state. And of course, this is the final post-quench state. So if you quench from this point to this point, the system has no quench at all, so the time to relax is 0. But if we move around this point, the system will start to relax, will need to relax. And the color you see here is the time needed for the system to relax to the final state. So usually, as long as more we move around this point, more the time will increase, but not in a trivial way. These lines here are isolines that show the same relaxation time. And now let's assume to move along this line here. Moving along this line means that the Euclidean distance is increasing because we are quenching more and more the two parameters. So the points along this line are far, far away from the final state. And if you look at this yellow star here and the blue star here, there is no Mpemba effect because this time is smaller than this time here. That is what we expect in a normal experiment. But due to the shape of this line, if we consider now these 2 points, the 2 yellow stars are on the same isoline, so they have exactly the same relaxation time. If you compare these 2 points, actually the blue star that is close to the equilibrium, the post-quench value, require a larger time respect to the yellow star that is here. So this is a Mpemba effect. If it's type 1 or type 2 Mpemba effect, it's not easy to be seen by this plot, but we have to look directly at the trace distance and produce the plot I showed you before. That means this kind of plot that are exactly produced for that kind of systems. Choosing different value of temperature and chemical potential, we can trigger or not the Mpemba effect of type 1 or type 2, or not having the Mpemba effect at all in general. Usually to do this, we need a quantum state tomography. We need to know the full density matrix to extract the trace distance. Sometimes we can see the presence or absence of Mpemba effect from other quantities. For example, from the current flowing across the system or from the energy inside the system, but this usually doesn't help to recognize the kind of Mpemba effect we have, type 1 or type 2, because if you see, when there is no Mpemba effect, the current of the cold system is smaller than the hot one. When this Mpemba effect is reverted, but there is no crossing in current respect to what we see in the trace distance. So trace distance is much more effective in detecting the Mpemba effect. We can find Mpemba effect in other kind of system. For example, we don't need to quench temperature at all. We can just play with the chemical potential of the 2 leads. And our definition also works for classical system. Indeed, this simple example where a quantum dot is coupled to 2 global environments reduced to a classical problem because the diagonal element of the density matrix decoupled from the rest and the Hamiltonian play no role at all. So this is actually a classical case with no temperature quench, but just chemical potential quench, where we can observe all kinds of Mpemba effect. But we can trigger an Mpemba effect also not playing with the environment, but playing with the Hamiltonian itself. So we can quench some parameter inside the Hamiltonian and observe Mpemba effect. A simple case is a superconducting Josephson junction, where we quench the phase difference across the junction. And here we have a plot of the relaxation time after quenching the flux across the junction from some initial value to some post-quench values. Of course, along the diagonal, we are not quenching anything, so the time is 0. But if we see that moving away from the diagonal, the time will not increase automatically. There are some special lines here where the time drops to 0, quite to 0. That means that there are some special quench such that the time drop down, and around these lines that we call it Mpemba arcs, we can trigger the Mpemba effect again, choosing 2 initial states that are across these lines. So the Mpemba effect is an effect that you can trigger just playing with initial state. You have to consider different initial states and see which one relaxes. But it's not that too smart properties, because usually we are not able to choose the initial state. Sometimes the initial state is fixed by nature and we have just to deal with it. And if we think about the original definition of Mpemba effect, the one given by Aristotle, actually Aristotle was much smarter than Mpemba. And there is a nice story written in the methodology of Aristotle, and this is a continuation of the sentence I said before. Aristotle says, yes, people know that hot water freezes faster, but people, to use this effect, first warm the water. Indeed, some inhabitants of Pontus, some fishermen of Pontus, when they want to put their fisherman rod on the ice, they first warm some water, pour it on the stick, and this will freeze faster. So the procedure will work if the time needed to warm the water and then freeze it is shorter than the time for cold water to freeze. Otherwise, it has no sense to spend time to warm the water. So Aristotle suggests a two-step protocol that is a bit different than the standard today Mpemba effect. It is a two-step optimization protocol that we call the Pontus-Mpemba effect for respect to the Pontus fishermen that use it practically. So what is this Pontus-Mpemba effect? Now we start with two copies of the system that are exactly the same properties, but also same temperature. Both of them are equal. And then we connect one of them to some freezing, directly to the freezing environment. So we want this cold water to freeze, and it will take some time, tau, from the starting to the final point. The other copy of the system is not directly connected to the environment, but it is connected to some other environment, some auxiliary environment, for example, a fire or the sun, that in principle will transform this, will change the state of this system in a time given by tau SA. But before this happens, so before the water can evaporate, for example, we decouple it from the sun or from the fire, and we connect it so after some shorter time, that the time needed to reach the equilibrium with this environment, we decouple the system with this environment. In the meanwhile, it changes the state, and we connect now with the freezing environment. And of course, now it will take some time to freeze. Let's sum up to the initial time needed to prepare it in this initial state. And if the sum of these two times is smaller than the time followed by the first copy of the system directly connected to the environment, we have Pontus-Mpemba effect. So it's a two-step protocol where we also consider the preparation stage, and it's nice because now the intermediate state that we have here don't have to be the steady state of some Limbladian or some environment. It could be just an intermediate non-equilibrium state along the trajectory to the final auxiliary state. So we have now we can use now a huge number, a bigger number of initial state for this effect. So what to do? Let's thinking about, again, the Aristotle definition. We have some starting state that is fixed somehow. We have a target state, a final state that maybe we can choose by ourselves. And the system under the effect of the environment will go directly from this state to this state, moving in what we call the velocity field. So if we have the trace distance, for example, for every possible initial state, we can compute the speed at which the trace distance will evolve. And this speed is only fixed by the environment of a steady state. So we can collect this velocity for every possible initial state, for every possible density matrix. And you see that there are regions that are slow, where the system evolves slowly, and regions when the system evolves faster. So if for some reason connecting the system to the environment forces the system to evolve in some region where the speed is low, this will take a lot of time to relax. And then we can use the Pontus-Mpemba protocol. We can say, let's connect the system to some auxiliary state A that have a different velocity field, the one shown here. Now the system will evolve along another line toward A. We interrupt this procedure somewhere here where it's convenient to us, and we will switch back to the velocity field of the environment, of the final state environment, and now the system can evolve to the final state moving through some region where the speed is faster. So of course, even if the total path is longer, you have to sum this green part and this yellow part, the sum of the two in terms of time is shorter. And this is when the Pontus-Mpemba effect triggers. And we can already observe it in a really simple system, a single quantum dot. It's the simple system because we can also represent it in the block sphere. So what happens? We have a block sphere, we have a starting point, we have a final point, and we have some auxiliary point, A. So under the effect of the final environment, the system will evolve along this red line. It will take some time. And this region, maybe the color is not so clear, but it's really slow region. The color is red of the velocity field. So here the system will slowly evolve from here to here. And if you look at the trace distance, is this red line here, monotonous red line here. It will take some time. Now we connect the starting point to an auxiliary field. So the system will evolve along another line, the yellow one, and eventually we go somewhere else, totally in some other point of the block sphere. Doesn't matter. Along this line, we interrupt the trajectory somewhere, for example, here, here, or here, and let the system evolve toward F from this point. And three cases can happen. If the auxiliary field driving the system toward the final point in a faster way with respect to the standard procedure, of course, when we release it, it will reach equilibrium faster because we helped it to go closer to the final point in some smarter way. So this is a Pontus-Mpemba effect, but we call it weak Pontus-Mpemba effect because it's quite trivial. We just help the system to go, we push the system toward the final state. But could happen that when we interrupt this procedure, actually the second copy of the system is far away with respect to the original copy of the system, but still closer with respect to the initial point. So in this case, the system could relax faster if the point where we release it here is in a region where the speed is faster. And in this case, there is a crossing between the standard procedure, the single-step procedure, and the double-step procedure. This is the yellow plus the green. And we call it in this case, Pontus-Mpemba effect, weak Pontus-Mpemba effect of type B. And then there is the most interesting case. It is the one actually described by Aristoteles. We drive the system somewhere else because we warm the system and we put the water on the fire. We are driving the system far away from the core, from a frozen state. So the point at which we release the system has driven the system far away from the initial point itself. So actually we put the system in a point that is far away with respect to the initial point with respect to the final point. But anyway, because the point where we free the system is in a region with high speed, the system will follow some route that eventually is longer, but at the end will require less time to relax. And again, this strong, what we call it strong Pontus-Mpemba effect, is characterized by some crossing between the two-step procedure and the single-line procedure. And again, if we can trigger or not this effect depends on the reciprocal position of the initial starting point, final point, and the auxiliary state. So if you look at the trace distances in general, we can have three cases. The blue one in this case is the trace distance of the single-step protocol. We connect the starting point to the final point, and the trace distance will decay. Then, if we look at the distance from the starting point to the auxiliary state, three things can happen. This first go down with respect to the blue one, and then go up, or this one stay always above the blue one, or in most general case, it can simply go away, and this is what Aristotle described actually. So the auxiliary state directly drives the system away. Now, as a function of where we choose the intermediate point here, we can trigger, in this case, weak of type A, weak of type 2, and strong Mpemba effect, only type B and strong, or only strong Pontus-Mpemba effect. This last case is the most difficult to trigger, but also the one that truly Aristotle described in this experiment, and but is not the most convenient for quantum state separation because it requires usually more time with respect to this case here. And of course, how many minutes? It's done. Okay, perfect. So just to say that we can generalize this approach and have more than one quench, and we can in general change the auxiliary state in time, and then we can trigger some continuous Pontus-Mpemba effect where we can play a lot with different parameters and search the best optimization protocol to reach the steady state. And actually stop here. And I just tried to describe two protocols, one based on the Mpemba effect, so on the initial state preparation, and one based on the relaxation procedure in a two-step protocol that can be generalized in more complex cases. And I stop here.
Okay, are there any questions?
Thanks, Andrea. So, very silly question. What is quantum in the quantum Mpemba effect? Like, and what I mean with that, I mean, of course, you are describing like with quantum theory, like a channel and so on, and Lindy-Bladian. But like, is there like any quantum effect there, like that speeds up, or like a coherence or something else that
Yes.
plays an important role?
Yes,
Or-
you have a competition between Hamiltonian and Lindbladian. So when you cannot have a Mpemba effect in the classical part of the Lindblad equation, the Hamiltonian can help to have Mpemba effect, or you can destroy it. So in the classical Mpemba effect, you don't have any Hamiltonian contribution in it. In this case, you have also contribution to the Hamiltonian that triggers different kind of trajectory into the state space. Yeah, we played a bit. You can trigger or destroy the Mpemba effect when you have an Hamiltonian. Yes, but you cannot how? Yeah, we didn't compare in this way. We compared the cases where we introduce or remove a piece of Hamiltonian to see if this trigger or not an Mpemba effect. We didn't compare directly classical Hamiltonian with the quantum one. But also the problem is that if you change the Hamiltonian, you are also changing the final state. So you are totally changing the protocol. So it's difficult to make a comparison in this sense.
But do you know if you generate coherence through these dynamics, or if it's like diagonal in some energy eigenbasis?
In principle, the diagonal elements are generated or are important for the Mpemba effect. There are cases in which they disappear, like the single dot connected to a global environment. In this case, actually, the diagonal element of the density matrix decouples from the rest, and you have a Pauli classical equation for the diagonal element of the density matrix. And this is more classical. But if your environment is local and not global, or is not a thermal environment, so doesn't satisfy the Taylor balance, in principle, the off-diagonal element play a crucial role in the evolution, yes.
If there are no more questions, maybe a quick one.
Have you considered the relative entropy rather than trace distance for comparing?
No, we just focus on the trace distance. Actually, you can replace the trace distance by any other function that is monotonous in the evolution and is bounded. This is also already proven in the Lue-Ratz paper that any function is monotonous decreasing along the evolution of so under the master equation. It is bounded, all predictor not Mpemba effect the same way. Only change the time at which you have not Mpemba effect, but this doesn't matter.
Thank you.
Okay, so let's thank Andrea again.